bağlandı. Asıl bir bağlansın, tekrar şey yapalım.
Tamamdır.
Evet. Habib, can you open your sound?
Okay. Open now.
Okay.
The video is also open.
Okay, everything is okay.
Okay, you can see me too.
Evet, bugünkü arkadaşlar sunumu Habib yapacak bize. Habib, kendini tanıtarak başlarsan devam. Okay. Let's start the presentation. Okay, let's start, please.
Okay. All right.
You have 15 minutes, right?
Okay, Ozan.
You have 15 minutes, including the questions, right?
Okay.
Right. Please start.
Okay. So I want to share the screen first. Switch camera. I want to share my screen to the audience.
I think you should share screen, right? Share screen, you know?
Yes, that's what I'm looking.
Screen, right?
Content, participant videos. Chat meetings.
You should press the share screen, please, and then continue.
Yes. Okay.
We couldn't see the presentation. Habib gitti mi?
Şu an bağlantıdan düştü hocam.
O zaman biz şeyi değiştirelim en azından. Şu an çünkü 7 geçiyor. Okay. We can continue. I think the second presentation. The title is The Investigation in Graphene Silicon-Based Schottky Junction Solar Cell. The authors are the Ala Jehad, right? Kemal Kocabaş and Metin Yurddaşkal.
Merhaba hocam.
Metin is here, right?
Yes.
Okay. We have 15 minutes to presentation and the question part, right?
Okay. Mm-hmm.
Okay, let's start, please.
I'm trying to share my screen, but it has disabled participant screen sharing.
Sorry, I couldn't hear you.
I'm trying to share my screen, but it
Okay.
seems like disabled.
We have a green.
Yeah.
Right, the share screen, right?
Yeah,
Press.
I mean, I need permission from the host.
Oh,
yes,
okay.
I can now.
Right.
Okay.
Okay, let's start.
Hello, everyone. Thank you for attending my talk. My name is Ala Jehad. I'm a PhD candidate student in Kocabaş University. My presentation title is Investigation in Graphene Silicon-Based Schottky Junction Solar Cell. I'm going to start my presentation to give a brief introduction about graphene, and then graphene use in solar cells, and then I'm going to move the Schottky junction between graphene and silicon. And the second part of my presentation, I will talk about my experiment work and result, and then I'm going to conclude my presentation with conclusions and references. The aim of this study to produce high-quality graphene layer by chemical vapor deposition method, and then fabricate the graphene silicon Schottky junction solar cell using different techniques. Graphene in solar cell can be used as a transparent conducting film used in amorphous silicon in indium gallium nitride solar cell. It could be used as an active layer harvesting material, they especially using it in silicon heterojunction solar cells. It could be used as a counter cathode electrode for di-molecule solar cell, and photoanode electrode in organic solar cells, and last, as a whole transporting material for hybrid organic inorganic perovskite solar cell. I'm focusing this study to make a Schottky junction between a graphene and silicon. So the Schottky junction simply is the interface between a metal and semiconductor, which is to provide a band bending to make the generated carriers like separated easier. Graphene in Schottky junction acts as an active layer, and this junction, we have a junction between the metal and semiconductor. This interface is make the separation of the generated carriers easier by the diffusion and the diffusion of the carriers like a drift at the junction. My experiment, I used two different types of silicon wafer, as you can see in the table. I used N-type silicon with orientation 111 and P-type silicon 100. And we synthesized the graphene by CBD methods, like we produce monolayer, bilayer, and tri-layers of the graphene. And we need also metals to make a contact for the cell. So we used like chromium, gold, and silver. Here we can see schematic view of the fabricated cell. First, we start with the silicon substrate. Our substrate is already coated with silicon dioxide, 100 nanometer. And then first we deposit the back contact, which we use silver, chromium, and silver. And then we deposit the gold frame as a front contact of the cell. After that, we etch inside the active area, we etch the silicon dioxide. And then the last step was transferring graphene on the top of the cell. The experiment work first was the preparation of the silicon substrate. As you can see in the image, we start first to cleave the silicon wafer to area 1 by 1 centimeter. And then it moves to cleaning step, which was, we used 3 different steps. First one was general clean. We used hot acetone and methanol, and then particle removal. We used the standard RCA method to clean the wafers, and then metal contamination removal. We used hydrofluoric acid, hydrogen peroxide. After each step, the silicon substrates were washed with rinse of deionized water and dried with nitrogen gas. Second step was deposition of the metal contact. As you can see the image, first we design a shadow mask with open area 8 by 8 millimeter. And then we first deposit the back contact, which was chromium with silver 5 to 150 nanometer. And then we deposit the front contact, chromium and gold. But as you can see in the second image, we cover the active area. We used like Kapton tape to cover the active area, which was around 4 by 4 millimeter. Next step was etching silicon dioxide. You can see in the image, we covered the solar cell with a Scotch tape, and then we open a small area, like almost 3.3 times 3.3 millimeter, and then we etch the silicon dioxide chemically using 1% of etcher for 90 seconds. And then wash the substrate and dry it with nitrogen. The synthesis of a graphene, we synthesize monolayer graphene or layer of a graphene with assistance of copper foil, gradually annealed at 1074 with the flow of hydrogen and argon. And then after annealing process, we open methane gas for 2 minutes. The next step was protecting the synthesized graphene. We used PMMA to protect the graphene with a spin coated at 2000 RPM for 60 seconds. And then to etch the copper, the copper foil, we soak the substrate PMMA, sorry, PMMA graphene and copper. We soaked in ferric chloride for around 40 minutes, and then we washed the samples for 3 times in deionized water, and then we transfer it on the silicon. So the last step was fabricating the Schottky junction. PMMA on graphene was transferred directly to the top of the silicon after etching the silicon dioxide, and we left it to dry in vacuum, and after that we need to remove the PMMA layer. So we soak the substrate or the cell in hot acetone for around 8 minutes, and after that it's dried again and was ready to make the measurement. First result I have is Raman spectroscopy. As you can see in the first, we have two plots. First, the black plot is indicating the producing of monolayer graphene. Here we use N-type graphene on N-type silicon. And for the second graph, we transfer graphene 3 times. So as you can see, the 2D band is become the intensity, like reduce the intensity and became wider. Here is the photo, like the image from Raman. When we use Raman microscope, we can see we still have small points, which is indicate the PMMA residue in the sample. Here is the second sample. We transfer graphene on P-type silicon, and again we here transfer for monolayer, and here when we transfer trilayer, we can see we have some defect, like increase the defect intensity. And still we can see here we have almost like, let's say, monolayer, and here we have multilayer, which be 2 or more. To make sure about Raman spectroscopy, we need to measure the 2 feature intensities, which first is defect intensity. As you can see here in monolayer graphene, when we transfer it on the N-type silicon, we got very low of defect intensity, and at the same time we got a number which indicates producing high quality monolayer graphene. Here we have the thickness layer intensity 2.7, which is indicate the monolayer. When we transfer graphene 3 times on the sample, we got like I to D over IG, it's 0.75. And the same happening for using P and for P silicon and N silicon. We are checking only the defect density of the graphene and the thickness layer ratio of the graphene layer on the substrate. The second result was for scanning electron microscopy. Here we can see from the image for SEM, we can distinguish 3 different colors. Here we have the gold, which is this part. The
last 5 minutes to finish the presentation.
Okay, yes. And here we have a graphene on silicon dioxide, and here the active area graphene on the silicon. Here the same, but we can see the wrinkles of a graphene on the same image. The third was only SEM on the active area. It's the same points we noticed in microscopic when we use it. And here for the second, when we transfer 3 layers of the graphene, we still can distinguish layers like metal, silicon dioxide, and silicon. And the wrinkles is more clear in this case because we transfer three times the graphene. And here we have the active layer, and we can see it's more dark and with lots of residue, PMMA residue. The last result is current voltage characterization. We can see here the first for monolayer graphene on P silicon. We have like low. Here we can see the efficiency of the cell. When we use P-type silicon, we got very low, very poor efficiency, 0.01, which is something normal when we use the P silicon because the majority carriers are holes. And for N-type silicon, the best efficiency we got is 0.2 when we transfer only 1 layer of graphene. Here is the second and the third. The challenges of the graphene Schottky junction, we have to make sure like the active area is only 0.11 centimeter. So when we increase this area, the quality of the junction will decrease. PMMA residue, we like normally we should use other techniques. Normally, they use deep ultraviolet to increase PMMA. And the design of the cell itself. Here's some suggestion for future work. We can texture the silicon substrate. We can make a surface modification and doping, and removing PMMA with other techniques. Conclusion: graphene silicon Schottky solar cell with top window structure has been fabricated. Mono and tri-layer has been synthesized with the assistance of copper foil. Raman shows high quality monolayer graphene with 2.7 thickness layer ratio. SEM shows the illustrate the morphology and the microstructure of the cell. And IV shows 0.23 power conversion efficiency in case of N-type silicon. And more investigation to understand the behavior of the cell will be continued. I would like to thank İzmir Katip Çelebi University Central Research Laboratory for letting me use CVD system to synthesize my graphene. Ege University Solar Energy Institute, they helped me with thermal evaporation system to deposit my metal contact, and with IV characteristic to measure IV characteristic. This is some of my references, and thank you for your attention. Any question?
Okay, thank you very much for your good presentation. And we have some times to discuss the presentation. If you have any question from the audiences, okay, we are waiting.
I have just a small question.
Yeah.
Right.
Thank you for your presentation. It's very interesting.
Okay.
Just I want to ask, there are another applications for the graphene silicon, this type of oil?
For graphene, normally if they use it as I mentioned in the second slide, if they use it as an active light harvesting material, it's the design I'm working on, like we're using Junction of the solar cell. But for me, I'm only using silicon, but other researchers, they're using multi-different of semiconductor, and they use graphene as an electrode or as an active layer.
Okay, thank you.
Okay, more questions?
Actually, I have a suggestion to remove the PMMA residues.
Right.
Maybe you can use low concentration of PMMA instead of using 4% of chlorobenzene. You can use like 1% chlorobenzene. And also for the heat treatment, after you coat your samples with PMMA,
Yes.
maybe without PMMA, no heat treatment, you can remove it more easily. Just try this.
Okay, I will. Thank you so much, Ozan.
Probably without heat treatment after the PMMA coating, it will be easy to remove all the PMMA residue.
Okay, I will. Thank you so much.
You're welcome.
Okay, thank you very much, Dr. Güneş, for your valuable comments on this topic. And okay, thank you very much, Ala, Jehad, for the good presentation. And Habib Amin, again here, 15 minutes ago, there was a connection problem. Habib is here, right? Habib? Habib is here. Hande Hanım, bir ses problemi olabilir mi Habib'le ilgili?
Hocam şu an burada geldi.
Okay. Habib.
Yes.
Okay, this is your turn
Okay.
for your presentation again. I'm here. And
Okay.
please start your presentation with sharing the screen.
Okay. I think I find the place now.
Right. Okay, we couldn't see your screen.
Okay. Can you see now?
No. we are waiting for your sharing. Okay. We see you, right?
Okay, but the sharing I shared
with the green button, right?
yeah, yes.
Okay. But select your presentation with the sharing screen. Select your presentation, PowerPoint presentation.
Okay. Okay.
We couldn't see again your presentation.
I think it's here.
No, we are watching your face, right?
Yes, but it's I'm sharing now.
Try one more time. If you have a problem,
Okay.
we will postpone your. Right.
Okay, nice.
Right.
Okay.
Yes.
Can I start?
Right. Please start.
Okay. Okay. Good afternoon. Okay, the topic of my presentation is the investigation of the effect of vacancy, or say defect, on graphene and hexagonal boron nitride implant heterostructure. So during the presentation, I will explain what graphene and hexagonal boron nitride implant heterostructure means. Okay, this outline. Okay, firstly, my research is to do with density functional theory. So it's like a computational material science, or say computational physics. Okay, and briefly, density functional theory is a computational method for solving Schrodinger equation. Okay, and what Schrodinger equation does is it's like a computational laboratory, like for computational material scientists that that use like to interpret the properties of atomic materials, to interpret them in the computational manner. So that's what technically DFT means. Okay, the fundamental of DFT, there are basically two fundamental theorems with regard to density functional theory. And the first one, what says is like the ground state of any atomic particles is the unique functional of an electron density. What that means is like, for us to find the ground state of any atomic particles, all we need is the electron density of that material. That's the first theory. And the second one says like, okay, how do we find that ground state? Then the electron density that minimizes energy of the overall function is the true ground state of that, your true ground state electron density. Okay. So introduction. This is how the structure looks like graphically. I divide them into two. We divide them into two. The first one is the hexagonal boron nitride substrate. Then we put graphene island as the middle of each structure. It is clear that hexagonal boron nitride HBN is an insulator, while graphene is a conductor. So by combining these two structures together, then we come up with another like hybrid material between insulating HBN and highly conductive graphene. So that's technically what my research is. So to find out how these two materials how can we tune, especially the band gap of this amazing material. Okay. So this is also, we also find so we also find out how the vacancy, affected this structure. We remove like one or more atoms of each, whether it is boron or nitrogen, and run the calculation and also see how the properties of this material changes in terms of the band structure, the electronic properties. Okay. Okay, the effect of vacancy, so remove one of the atoms, whether it is boron or nitrogen. Also carry out all the self-consistent calculation for the K-point mesh and all the convergence. Okay, so the methodology, the software that we use is VASP, that is Bena Initial Simulation Package. It's the popular software that's used by computational material scientists and computational physics for running density functional theory calculation. We perform PFT by adopting the GGA together with the PW91 for the exchange correlation potentials. Okay. Yeah. Also, during sampling, this is all the processes that we follow for the K points and for the HPN. This is the dimensions, 8 by 8 by 1. I mean, all the details are here been explained. Okay. The adapted criteria that we use, energy convergence and total forces on each atom, also they are listed. Okay. Also carried the spin polarized and non-spin polarized calculations also. Okay. For the pristine samples and also for the defective one. The pristine one is the pure sample without any defects, while the defective system is the one that whether we remove maybe boron, nitrogen, or carbon, just one atom, and also run the calculation to see what is the difference between the pristine and the defective one. Okay. Okay, you can have it in the mission of whether it's carbon, boron, or nitrogen. We run the calculation, we see what happened. Okay. So the result that we obtain, what we concentrate is first is the magnetization energy, to see how the structure magnetically. When we say magnetization energy, we mean since we run the calculation for the spin polarized and for the non-spin polarized, so we the difference of the total energy between the non-spin polarized calculation and the spin polarized calculation is what gives the magnetization energy. So if the magnetization energy is high, it's showing us that this our system is like suitable against maybe thermal fluctuations. So it will be suitable even if the temperature rises, something like that. Okay. Then also the island formation energy. That is the island that we put here. If it is a graphene substrate, by putting HBN island, it means we are removing carbon atoms and replacing them with either boron or nitrogen to create this island. So the energy that is needed to break down the carbon bond and replace them with either boron or nitrogen to create the island, that's what refers to as this island formation energy. Also give us the glimpse of how different island sizes affect this structure. Okay. Then the defect formation energy. The actual, if we remove boron or carbon or nitrogen, what is the effect? What is the total energy of the system? How the total energy changes if it is boron that is being removed or carbon or nitrogen. We also study that. Okay. Also, structural construction was not observed after the optimization. Like the structure remained mostly intact, no like distortion on the bonds and other stuff. Also, structure remained like intact. The interface is energetically most favorable for the generation of mono vacancy. So the interface, that's the border between the island and the substrate. In between, that's the HBN and the graphene. That's the most important area that determines the properties of this new material. Okay, so this is some of the results that we get. As I mentioned, the island formation energy is here. the defect relation is also here, and also the band gap. I will explain maybe in the next slide how these numbers affect the properties of the material. So in this bigger table, as we can see, the ones with the green highlight are the ones that we concluded are the most stable structures in the system, because they are the ones with the highest magnetization energy, which means they are suitable against thermal fluctuation. Even if the temperature changes or some distortion from the outside distortion, still the structure remains intact. Okay, and also how the band gap changes. You can see clearly the band gap changes. The bigger the island size, the smaller the band gap. Okay, so visual comparison also. The one in the first three are the ones with graphene substrate and HBN island. The ones with the like flat band gap. Well, those structures are the last three ones with these contours are the ones with the HBN substrate and graphene island. So
In last 5 minutes, right?
you said?
Last 5 minutes.
Yeah, yes. I'm
Right.
about to. Yeah, it's already done. Yeah.
Oh,
Okay, so this is my presentation. If there's any question, I will be glad to answer.
Okay, right. This is the early finish, right? 5
Yes.
minutes you have, in fact. Is there any question from the audience? To good presentation. Thank you very much, Habib.
All right, thank you, sir.
Is there any question from the audience? Okay, I think no question.
Okay, thank you very much.
Right, we have in fact 1 or 2 minutes, right? My question is, what about your career planning as a student, right? You
Yeah,
can mention about this,
my career plans.
right, about this topic.
Yes, actually, it's material science, and also I'm also a lecturer at university in my home country. So this is what I will continue to do my research on, and hopefully pass it on to my students. And it's like I'm taking the knowledge here. Actually, very few people, I believe, back home in my country, this is specifically computational material science like this one.
Okay.
So,
What do you think about the Schrödinger equation? You like it?
yes, of course.
Right.
I mean, it's a
You
computational.
are right. You are working on this, right?
Yes. Yes, I am.
Okay, thank you very much. Good luck in the science, right?
Thank you very much. Appreciate it.
Okay. This is the third one. Stochastic optimization of friction stir welded aluminum alloy joints by using neuro-regression approach for maximum tensile strength. The authors are Gülperi, Feyza, Yavuz, Levent, Aydın, Melih, Savran, Ozan, Ayaktaş, Harun Sayı, and H.Seçil Artem. The presenter, Gülperi, Feyza, Yavuz is here. Right. Okay, Feyza. If you okay, we can start, right?
Tamam, paylaşıyorum hocam sunumu.
Evet, görülüyor şu an.
Tamamdır.
Evet, başlayabiliriz.
Hello, my name is Feyza, and I'm a postgraduate student at İzmir Katip Çelebi University of Material Science and Engineering Department. And now I'm going to present you stochastic optimization of friction stir welded AA7039 aluminum alloy joints using neuro-regression approach for maximum tensile strength. Sorry.
Okay. We are watching your presentation.
Okay. And this is my outline, as you can see. On the right side, friction stir welding shown schematically. Before starting the presentation, I want to talk about friction stir welding working principle. And when we look at the arrows, the green one indicates axial force, and the blue one is rotational speed, and orange one is show welding direction. And rotating shoulder creates, you can imagine that this pencil as a rotating shoulder, it creates some friction, heat, and welding pressure. When the shoulder moving through the direction, two parts are joined. And let's begin with motivation. Friction stir welding is a solid-state bonding process that are used as a tool to join two workpiece material without melting them. The heat is generated by friction between the rotating tool and the workpiece material. The rotating tool and the workpiece material creates a softened zone near the friction stir welding tool, and the two parts are joined each other. So while the tool is moved along the joint line or welding direction, two material pieces are joined each other through friction. And this process is used in aviation, shipbuilding, marine, automotive and rail industry, and similar fields. The motivation of the study is that a technique is used in such a wide area to improve the process and obtain the optimum outputs by saving time and cost via using neuro-regression approach and optimization methods. These are our objectives. First one is to maximize the tensile strength of friction stir welded AA7039 aluminum alloy joints. And the second one is investigate the effect of parameters such as tool rotational speed, welding speed, and axial force on the tensile strength. And third one, to perform a suitable model using neuro-regression approach and obtain optimum values through stochastic optimization methods. Optimization is the mathematical process to find the minimum or maximum output. And in this study, some optimization algorithms used, and these are shown with blue in the diagram. In our study, there are starting constraint values. The friction stir welding process is a static problem. And here we have a one objective function. And in this objective function, we check the design variables in the range of continuous and integer scale. And stochastic optimization methods were used to obtain the optimum volume. Statement of an optimization problem. This slide explains that there's only one objective function we had. So we can say a single objective optimization problem. Problem definition. With this table, we can define the problem. There are three design variables in the single objective problem. And these are x1 is rotational speed, x2 is welding speed, and x3 axial force. And on the side, there are minimum and maximum values are shown. And the aim of the study is to maximize the tensile strength. When we look at the constraint section, scenario 1 describes the continuous range, and scenario 2 describes the integer range. And a flow chart shows the stage that we followed in the study. First, we start with the data selection, and then a model was created and boundedness check of this model was done, and certain optimization methods were used to achieve the optimum volume. And this is reference study. We use the data of this reference study. In this study, response surface methodology and artificial neural network approach were compared with each other. Problem definition. Our data are represented in table. Yeah, we divided the data as 75% training and 25% testing data to acquire a model by using Neuro-Regression approach. The non-Neuro-Regression model is constituted using training part, and the remaining parts of the data are used for tests. By using Neuro-Regression approach, we obtained a multiple second-order non-Neuro-Regression model. And this is a second-order function. And tensile strength represent as a Ts, and rotational speed N, welding speed S, and axial force is F. Yeah, for this study, R-square training value is found 0.99, and testing value is found as a 0.97. R-square can take a value between 1 and 0 and 1, and values above the 0.85 can be accepted according to the engineering application to be used. And as can be seen here, our results are good and within this limit. And to evaluate whether the proposed model bounded or not, the maximum value is 319.91, and minimum tensile strength value is 169.78. These results are appropriate for defined problem. In this regard, it can be said that the proposed second-order multiple nonlinear model is usable for friction stir problem, which is handled in the study. And 3D graphs, these are. These 3D graphs of tensile strength results for the proposed model and observed experimentally is given in here. It is seen that the proposed model fit well with experimental results. Red dots are represents the experimental data, and the yellow area represents the proposed model. And we keep the axial forces for A 8 kilonewton, for B 6 kilonewton, and C 4 kilonewton. The other results. We use different algorithms for the same problem to make our results more reliable. These are Nelder-Mead, simulated annealing, differential evolution, and random search. When we evaluate the results we obtained from these methods, we see that the results for the continuous range that are the same. It's all same, and the global optimum value is 319.91. Due to the precision of the rotational speeds, and welding speed and axial force, we have achieved in a continuous range. It is likely to be difficult to apply it in terms of engineering.
Last 5 minutes.
Okay. Therefore, we optimized some problem in integer range. When we look at the table, it's seen that the tensile strength values are 319.87, and for another mid and differential evolution, and the other one is 319.84 for simulated annealing and 316.82 for random search. So this table indicates that since the difference is very small, if we cannot work the continuous range, it can also be worked in the integer range. In this paper, has focused on a solid strength joining technique, which is a friction stir welding. A regression model was developed to obtain the maximum tensile strength value of AA7039 aluminum alloy joints by considering some important friction stir welding parameters, which are rotational speed, welding speed, and axial force. Also, artificial neural network and response surface model were used in the main study where data were obtained. And a better results was obtained compared to the response surface model. And according to the ANI results, a very close but slightly better value was obtained. This study proved that the stochastic optimization methods give a reasonable approximation for relevant joining technique by using neuro-regression approach. And this is the end of my presentation. Thank you for your listening.
Okay, thank you for your good presentation, Feyza. Is there any question from the audience? One question maybe is possible. Right, Elif from Melih, right?
Yeah, I have a quick question to Ms. Feyza. While defining the optimization, you said, or maybe you consider the system as static. Why did you consider the system as static since we have a tool and a plate? I think that we have rotation and we have a motion. Why did you consider it as static?
I couldn't understand, I'm sorry.
Can you quickly open your presentation? You have optimization. When you define optimization, there is a diagram there.
Mm-hmm.
And then in the diagram, we had a dynamic or static. You defined your problem as a static problem. What did you define it like that? Since we have a tool and we have like a motion, we have rotation and a motion. Is there a reason for that?
Because of motion, I couldn't answer that.
Elif, I can answer your question. It is about the optimization theory, right? And
Yes,
dynamic concept is different from the motion, the time dependency, right? It is a conceptual problem and conceptual. And if your design variables are changing, right? Design not constant, are changing. If they are changing, right? This is called as a dynamic optimization problem. It is not related to motion and dynamic problem. It is just same words, right?
Thank you. I understand that. So it's not related to the
motion
of the tool or plate. Right. Okay. Thank you, sir.
Okay. Right. Okay. Thank you very much for the audience. We can continue with the fourth one. HDP'nin mekanik özelliklerine karbon elyaf ve çayın etkilerinin incelenmesi isimli bir başlıkla katılıyor yazarlar. Gözde Turan, Çağla, Ceren, Aydın ve Münir Taşdemir. Sunum yapacak olan arkadaşlardan... Anlaşılamadı. Evet, bu Gözde Tuğran, Çağla Ceren ya da Münir Taşdemir ekibinden bir kişi var mıdır? Sanıyorum yok. Hande Hanım, bir bilgi var mı? Yok herhalde.
Hocam gelmişlerdi sanıyorum ama bir tekrar teyit edeceğim.
Tamam, 2001 numaralı diye not alınmış burada ama
Evet.
bu da aslında. Şöyle mi yapalım? Konuşup ses alamıyoruz herhalde şu an.
Evet, ses alamıyorsak hocam bir sonrakine geçelim isterseniz. Çünkü şu an
Tamam.
göremiyorum. Seslerini duyamıyorum.
Tamam, anladım. Şu an bu şekilde yapamıyoruz. O zaman bir sonraki, the fifth presentation is about the stochastic optimization of the graphene sheets subject to drilling using Neuro-Regression approach for maximum mechanical strength. Evet, Bartu Aydın burada mı acaba sunum için? Bartu Aydın sunacaktı. Şöyle, aslında normalde 5 dakikası var tabii. Biz 5 dakika geriden geliyoruz. İstiyorsanız bekleyelim. 5 dakika içerisinde bağlanırsa.
Hocam bir sonraki Davut Ali Aser burada galiba. İsterseniz
Öyle mi?
müsaitse
Tamam, öyle
Davut'u
yapabiliriz.
alalım.
Tamam, olur. Davut Ali Aser burada mı?
Yes, hocam. Yes, I'm here.
Okay. We can continue with your presentation.
Okay.
The unit root test comparison in the presence of the structural breaks. Please start, and you have 15 minutes, right, including the questions.
Okay, thank you.
Right, good luck.
Can you see my screen?
Yes.
Okay, thank you. My name is Daud Ali Asif. I'm from Somalia.
Davut, please
Yes,
make it full screen.
Okay. How about now?
Okay.
Okay, thank you. I'm Daud Ali Asif from Somalia. I'm PhD student in statistics at Hussain University. My supervisor is Prof. Dr. Esin Feruzan. My topic of presentation is about unit tests comparison in the presence of structural cracks. It is time series analysis. The outline of my presentation contains introduction about the topic. Then we test the presence of structural cracks using two tests, Chow test and Hussain test. Then we will test also unit root test using 3 different tests. After the theoretical background of those tests, I will apply those tests in stock prices data. Then conclusion will follow. Let me start with introduction. Time series data, we usually experience unexpected change in the dynamics of the data. Those changes can be in the mean of the data or a trend, slope, variance, or the intercorrelation structure. The changes may be because of policy change, financial crisis, natural disasters, technological improvement. For example, as we are now in the period of coronavirus, almost every financial trend change, and many studies shown that most of the important indicators, economic indicators, have structural breaks in one way or another. Here we shown some types of structural breaks. This one shows structural break in the trend. There is also a structural break in the level or intercept of the data here. The fourth graph shows structural break in both, in the level and the trend. And this graph shows the impact of structural break in the forecast of the data. If we don't consider it well and shown in the model, consider in the model, then we will end up forecasting like this way, while the trend goes this way. The possible challenges we need to consider when we are modeling structural breaks, we need to know how many breaks we have, whether it is one or multiple. We need to know also break's location, where the break is, whether it is endogenously or exogenously, and the type of the break, whether it is in the level, slope, or both. We start with the test, the presence of structural break. The classical test is called Chow test. It's proposed by Gregory Chow in 1960. This is to test the equality between sets of coefficients in two linear equations. In time series, we use to test for the presence of structural break at a predetermined period. So we need to know the place of the break before we apply Chow test. The null hypothesis here that there is no structural break at the given point. This test considers a linear model split into samples at predetermined break point. So the first regression model is before the break point TB, and this the second one is after the break point, since we determined the break point. So we compare the parameters of the two models. Chow test estimates coefficients for each period and uses out of sample forecast error to compute F test, comparing stability of the estimated coefficients across the two periods. The other test we applied here is Hussain test. It's a cumulative sum model. This has been proposed in 1976. And the null hypothesis is the existence of structural break. This test is for the instability, is appropriate for testing parametric instability in the intercept term. It is used as the test for instability of the variance of positive regression residuals. This is how we model when we use the custom test, and it is computed from one step ahead residuals of the recursive least square model. It is based on the intuition that beta changes from one period to the next. Then one step ahead forecast will not be accurate, and the forecast error will be greater than 0. Coming to the unit 2 tests, we will apply 3 unit 2 tests to compare the results. The first one is decafuller, and it is augmented decafuller. Decafuller is based on autoregressive model 1. Only 1 lag, it considers 1 lag. And we assume that the error term is distributed as normal with mean 0 and variance sigma square. What we are testing is that the phi, the parameter here, is whether it is equal to 1 or not. Sorry. So that
last 5 minutes, right? Last 5 minutes to finish the presentation.
Okay. So here we test whether this phi is equal to 1 or not. That is where unit 2 is coming from. Sometimes can be written as lambda, that is phi minus 1. Augmented decafuller test is the generalized decafuller test, not anything more. And we have 3 kinds of models. One is pure random walk. The other one is considers drift, it has intercept, and the second one has trend. The other one test we are going to consider is Phillips-Perron unit test. And and this is the model we are going to consider it. The third test is Ribot-Andrews test, and this one is the one considering structural break, and it has three types of models. One considering intercept, second one trend, third one both. Here is the application. We are applying stock prices, open prices of 5 years weekly data. This is the graphical representation of the data. It shows that it has some priorities. Here we tested the presence of structural breakage using chow test, and it shows that 2016 and 2018 in the second and 22nd week there are breaks, and so we can reject the null hypothesis that there is no structural break. Some tests also agrees that there is a structural break. Coming to the unit tests, augmented Fuller, when we apply in the level data, it shows that the data is not stationary, but after differencing one difference, it shows that it is stationary data, so there is no unitary test. PB test has both the same results as ADF test, while Ribot and Andrews unitary test also gives the same results, but in addition, it shows the break location in both types of data. Conclusion is that shell test, custom tests are used to test the presence of structural breakage. Both tests show that there are structural break in the data. The unit 2 tests of ADF, PB, and Ribot Andrews test also shows that the data is not stationary in the original form, but after differencing, it shows stationarity. Ribot and Andrews also specifies the places of structural potential break points. And that is all. Thank you for listening. These are the difference.
Okay, thank you, Daud, for your presentation. Do we have any question from the audience? Only one question is possible because of the time. Any question? I think no. Then we can continue with the Bartu Aydın presentation. Bartu Aydın is here. Bartu.
Yes, I'm here.
Okay. Bartu, the title of this study is, let's read again, the stochastic optimization of graphene sheets subjected to drilling operation using neuro-regression approach for maximum mechanical strength, right?
Yes.
Okay, we can continue with your presentation.
Okay. Can you hear my voice clearly?
Right, everything is okay.
Okay.
15 minutes and including the questions, right? Don't forget.
Okay.
Right.
Hello again. I'm Bartu Aydın and a postgraduate student at İzmir Katip Çelebi University, Department of Material Science and Engineering. We studied on the stochastic optimization of graphene sheets subjected to drilling operation using neuro-regression approach. This is the outline of our presentation, and I would like to start with the motivation part and continue with the other parts step by step. Let's start with the graphene material in general, and it is a two-dimensional sheet of sp2 hybridized carbon, and it's in the honeycomb lattice structure. It ensures some kind of unique properties, and it has been center of interest because of that. In the drilling process of graphene has come forward as an important issue since increasing demand to manufacture of nanocomposites in aerospace, defense, and electronics. So estimating the parameters by using the mathematical modeling for this kind of process and optimization methods would be useful for saving time and decreasing production costs. We can refer our objectives like that to obtain the maximum mechanical strength of graphene sheets subjected to drilling operation, and to examine the effect of design parameters such as temperature, drill bit velocity, and feed rate of the drill bit on the mechanical strength of graphene sheets. And also, we wanted to generate a reliable model from data by using Neuro-Regression approach and acquire the valid optimum values by using stochastic optimization methods. Herein, this is a general definition of optimization. We can define it that it is the mathematical process to find the minimum or maximum output. And you can see at the bottom the table of the 6 categories of optimization algorithms. And the red boxes represent algorithms that are in our problem. We defined some optimization problem having some constraints, and this is a static process. And our problem has just one objective to reach. That's why we call this kind of optimization problems as single objective problem. And we check both continuous and integer intervals of design variables. And also we formed a model by using Neuro-Regression approach, and it became our objective function. Finally, we carried out the stochastic optimization methods to reach optimum values. We can see in this page 2 types of the optimization problem as single objective optimization and multi-objective optimization. As mentioned before, our problem has just one objective, so it is a single objective optimization. To carry out any optimization problem, objective design variables and constraints are specified, and for objective, it could be minimizing or maximizing something, and in here it is represented. The objective function is represented by f, by the function of f, which depends on the thetas, and they are represented as design variables. Also, constraints are represented as g and p in here. We mentioned about the single objective problem of ours, and we can define our problem as maximizing the mechanical strength of graphene sheets at certain parameters such as temperature, feed rate, and rotational velocity. And these are our design variables and represented in here x1, x2, and x3 respectively. And they can take some certain values, such as temperature could be between 300 to 600 Kelvin, and feed rate could be between 10 to 30 meter per second, and so on. Also, our aim is that maximizing the mechanical strength. So we can see our objective function ms in here depends on the variables x1, x2, and x3. And also we can mention about 2 situations in the constraints parts. In the first scenario, design variables can take values in a continuous range, and the second one, while in the second one, they take values in integer range. You can see the flow chart of the whole processes. and it is started with the data selection and continued with forming a model. After that, accuracy of the model is checked as a first step. And if there is no problem until here, some design optimization methods are selected, and finally, optimal solutions are reached. And this is our reference article, and we use the data of this reference article. Here, and in this study, multi-gene genetic programming approach were proposed and compared with the artificial neural network. And in here, some of our data were taken from an article are represented in table. We have 63 data in total, and since forming a model by neuro-regression approach, we divided the data as 70% training data and 30% testing data. The multiple nonlinear regression model is constituted using training part of the data, and the remaining part of the data are used for testing. By using training data, multiple nonlinear regression model for mechanical strength has been as follows. And this is a third order model function, and you can see at the bottom that temperature is represented by T, feed rate by F, rotational velocity by R, and mechanical strength by MS. This is our objective. And in here, the statistical accuracy of the model is shown in table. R square for training and testing are found as 0.9838 and 0.9636 respectively, and for R square adjusted, we can see from the table, and training and testing values are like that, and they are almost 1, and we can say that it is okay for our process. And but in order to determine whether our fitted regression model is bounded or not, we carried out a boundedness check of the model by checking the maximum and minimum values in the search space of design variables specified in this study. The values of strength are obtained as 18.02 as a minimum and 115.6 gigapascal as a maximum. Since the model gives realistic results in the manner of engineering, it can be interpretable as bounded for this study. In here, there are some 3D plot representations of comparison between experimental and recommended model results on mechanical strength in terms of temperature and rotational velocity. Feed rates are taken in here as 10, 20, and 30 meters per second, respectively. You can see from the graphs, red dots represent the experimental data, and the yellow area represents the proposed regression model. And we can interpret this kind of 3D plot representations that the proposed model fit well with experimental results because yellow area overlapped with red dots. And this is our result table, and and shows us the optimum mechanical strength of graphene sheets utilizing stochastic optimization methods, considering both continuous and integer search space for design variables. And
Last 3 minutes, Bartu.
Okay. We carried out the methods Nelder-Mead, simulated annealing, and differential evolution, and random search. These algorithms work independently of each other, and so we can interpret obtaining the same values in all algorithms. They are global optimum values for this study. Consequently, optimum mechanical strength was found as 115.6 gigapascal at 300 Kelvin, 10 meter per second, and 50 radian per second, which and these values are the same value with the reference article. And it has been understood that the interval values of design variables do not provide higher mechanical strength for drilling operation problem solved in this study. Also, this study demonstrated that the stochastic optimization algorithms give a reasonable estimation of output variables at certain parameters by using the Neuro-Regression approach. And thank you for your attention. If you have any questions, I would appreciate to answer.
Okay, thank you very much for your good presentation, Bartu. This is a study with the collaboration of the material science and mathematical modeling. From the audience, is there any question? Is there any question? I think no. No, right. Thank you very much again.
You're welcome. Thank you.
Okay. As a last presentation, Gözde Turan, Çağla Ceren, Münir Taşdemir burada mı acaba? Tekrar bir soralım. Katılım yoktu. Evet, sanıyorum burada değiller. Ben göremedim. Hande Hanım, var mı bir gelişme? Yok herhalde. Tamam, o zaman bu sunumu yani bu session'ı kapatıyoruz arkadaşlar. Tüm gelen misafirlere ve sunum yapan tüm katılımcılara teşekkür ederiz. 15 dakikalık bir aradan sonra saat tekrar 15.45'te session'lar başlıyor. 3 paralel session şeklinde. İyi çalışmalar herkese dileyelim. Görüşmek dileğiyle.
Görüşmek üzere.